Kia ora. This video is a request for Hann and it's out of the textbook, but I'm going to combine it with a question that I've made up myself. So this is from the textbook chapter back when we didn't know what polar form was, when we were just working with rectangular complex numbers. And it's about cubics, right? So we're asked first of all to expand and simplify this, and then we have to deduce that if this complex number, so z cubed, is real, then either this must be true or this must be true. And from there, we have to go on to find all of the complex numbers for which z cubed is equal to 1. So we're basically being asked to find the complex cube roots of 1, but we're working entirely in rectangular form. Now, if you saw that question now, hopefully, if you just saw solve z cubed equals 1, then what you would do would be immediately think about doing it in polar form. So that's what I'm going to start out by doing. Right, so we've got z cubed equals 1. We're going to start by saying let z equal r cis theta. So r cis theta to the power of 3 is equal to 1. Now we can write 1 as cis of 0 plus 2n pi. Right, so 1 is sitting out here, and the angle, the arg for that complex number 1 is 0, or we can think of it as 0 plus 1 revolution, or another, or another. That's how we're going to generate our three solutions. By applying de Moivre's theorem, we get r cubed cis 3 theta is equal to 1, I'll put that in, cis 0 plus 2n pi. R cubed is equal to 1, so r is equal to 1, right, because r is real. And then 3 theta is equal to just 0 plus 2n pi. So that generates theta is equal to 2n over 3 pi. And we're going to get 3 roots, so z1 is when n is equal to 0. So we've got z is equal to cis 2n pi on 3 for my three solutions. So z1 is where n is 0, so z1 is just cis of 0, which is 1. z2 is equal to cis of 2 pi on 3. Now, if we look at what that is, that's just one of our special triangles. Okay, so there's 2 pi on 3 here, 120 degrees. And we know that this will be -1, and this will be root 3, and that will be 2. So we can leave it like that in polar form, but in rectangular form, it's going to be -1. Let's think. No, it's not going to be that, because we know, of course, sorry, having a slow brain moment, done a bit much YouTubing today. We know that r is 1, right? So this is on the unit circle. So if that's 1, this is -1/2 for that coordinate there, and it's root 3 on 2. Okay, so I've taken my special triangle, just for those of you who found that a little bit fast. Here's my special triangle, my 1 root 3 2 triangle, but this is not going to sit on the unit circle. This is going to sit on some huge circle with a radius of 2. We want the similar triangle that has a radius of 1. So the baby triangle where everything's scaled down by a factor of 2. So 1/2, 2 over 2, which is 1, and root 3 over 2. So here we've got -1/2 plus root 3 on 2i. And the third complex number here is going to be cis of putting in n equals -1, cis of -2 pi on 3. And cis of -2 pi on 3 is going to sit, so we've got 1 here, one solution here, 1 here, and we've got the third one down here. So remember, the roots are symmetric. And the coordinates for this one will be -1/2 minus root 3 on 2i. Okay, so if you were just given that question to solve, I would be hoping that almost all of you by now would be using polar form to do it and recognizing how useful de Moivre's theorem is for the step from here to here. But this question doesn't do that, and it's quite good practice at understanding rectangular form. So let's finally, 4 minutes in, Hann, sorry about that, hope you're still there. I'm going to go through the textbook question, which is doing that in rectangular. So we have to expand and simplify a plus ib cubed. And that's just good basic practice at a binomial expansion from AS. So 1, 1, 2, 1, 1, 3, 3, 1 for my coefficients. It'll be a cubed plus 3a squared times ib plus 3 a times ib all squared plus 1 times ib cubed. Expanding that, I get a cubed plus 3a squared bi plus 3a b squared I squared plus b cubed I cubed. I'm going quite slowly here to make sure that everyone in the class is comfortable with those powers of I. Remember, my goal is eventually to group the real bits together and the imaginary bits together. So here we've got a cubed for here, and we've got another real bit here, minus 3ab squared. Here I've got plus 3a squared bi. And in here, the I cubed is equal to negative I, right? Because the I squared is negative 1. So 3a squared b minus b cubed I. Right, so we've done that first bit. And then we're asked to deduce that if this thing here is real, then either this is true or this is true. So if it's real, then the imaginary part of a plus ib cubed is equal to 0. That means that 3a squared b minus b cubed equals 0. So b into 3a squared minus b squared is equal to 0. So either this is 0 or this is 0. Is that what we're asked to write? Oh, yeah, that's right. We're asked to write it like that. Good. Okay. Hopefully you think that's good. I think that's good. There. That's the first bit done. Now let's look at this last bit. Hence, in other words, using the thing you just did, find all the complex numbers z for which z cubed is equal to 1. Now we know that there are going to be 3 of them, and we know that what we're going to have to do is to use that result with all the a's and b's. So I'm just going to get rid of some of this stuff here. I suppose I could just go to a new page. That would have been easier. Right, so what are we trying to do? We're trying to find the solutions for z cubed is equal to 1. We're going to start by saying let z equal a plus ib. We know that a plus ib cubed must equal 1, and I'm going to write that as 1 plus 0i. So from the thing we just did, we know that if this is a real number, right? So if we know that this is a real number, then either b is 0 or this is 0. So we're going to work with 2 cases. So this is a lot like what we've been doing in some of the scholarship calculus sessions. The first case we're going to do is case 1, and we'll do the easy one first, when b is 0. So if b is 0, then z is equal to a plus 0. And that means that a cubed is equal to 1 and a is equal to 1. Right, so I'm taking this substituting in b, and then I'm substituting it in here. So that's easy, and we kind of knew that 1 cubed was 1. Case 2 is that b is not 0 and 3a squared is equal to b squared. (3a squared is equal to b squared. So look at my expansion of the complex number that we had up above. We had a plus ib cubed is equal to a cubed minus 3ab squared plus 3a squared b minus b cubed I. And we know that this has got to equal 1. Oh, sorry, this has got to equal 1 plus 0i. So I'm going to work with this first of all. We have a cubed minus 3ab squared is equal to 1. And we can now substitute this. So we know that b squared is 3a squared. So substitute directly for that, and we get that 3a squared equals 1. I get a cubed minus 9a cubed is equal to 1. Negative 8a cubed is equal to 1. A cubed is equal to negative 1/8, and a is equal to negative 1/2. Substituting that back in, we now need to find b. So a is equal to 1/2. We know that 3a squared equals b squared. A squared is equal to 1/4. 3a squared, I'm going really slowly here, so 3a squared is equal to 3/4. 3/4 is equal to b squared. So b could have been either a positive or a negative number. B is equal to √3 on 2 or negative √3 on 2. So all I'm doing there is I'm squaring that. So that has generated for me the other two solutions. So Z2, our second solution, is negative 1/2 for A plus √3 on 2i, and Z3 is equal to negative 1/2 minus √3 on 2i. Okay, so that is quite a good brain workout on proof stuff. I think that question is worth going over for everyone, just when you're getting towards the end of your complex numbers study, okay, because it really makes us think a bit about using rectangular form instead of just switching into polar. So Han, thank you for sending that question in. Most of you have done that question, but for some of you who haven't tried that one yet, that might be one to put on your list, and then remember to update the tracker sheet once you've had a good go at it. I'm quite happy for you to update the tracker sheet after you've watched this video and made sure you've worked through the question. Thanks for watching, guys. I'll do some of the excellence questions later on.